Okay, energetics of solution formation. We can think about this as happening in 3 steps. So the first thing that has to happen is we have to separate the solute particles from each other. Okay, so the solute particles are held together by some sort of intermolecular force. So separating them is going to require putting in energy, right, to break those intermolecular forces. So that's going to be endothermic. Energy is required. So we'll call that delta H for the solute, and that's greater than 0. Separating the solvent particles, also endothermic, right? So this is going to be positive. And then when we mix the solute and the solvent particles, that's going to be exothermic, because now we're forming interactions between the solute and the solvent. And so that's delta H for the mixing, and that's going to be negative. Remember, negative is going to be something that happens, and positive most likely not. So the enthalpy of solution, the heat or energy change by forming a solution, is the sum of those changes. And the overall sign of that will depend on the magnitudes of the individual terms, because we have 2 that are negative and 1 that's positive, 2 that are positive and 1 that's negative. So forming a solution can be exothermic or endothermic, can release energy or absorb energy. So here we're looking at a solvent and a solute, and we have to separate the solute particles. That requires putting in energy. We have to separate the solvent. Separate the solvent, separate the solute. Now we've got separated particles, and when we allow those to mix together, energy is released as attractions are formed. Here we've got the same sort of situation, except now when the energy is released, this release of energy is less than the total amount of energy that had to be put in. So this is going to be an endothermic process, and this will be an exothermic process. And whether it's exothermic or endothermic just depends on the relative sizes of these 2 terms and this term. Does that make sense? So mixing ionic compounds into water, what we can do is we can combine delta H for the solvent and delta H for the mixing. So this is the separating of the water molecules and the formation of the mixture of the interactions between the water and the ion particles. We can call that the heat of hydration. And that's defined as the enthalpy change when 1 mole of a gaseous solute in the ion form dissolves in water. So that incorporates the water molecules having to separate and the association of the water with the ions. It's always going to be exothermic. Delta H for the solute, separating those ions, is equal to the lattice energy but opposite in sign. Remember, lattice energy was when we had ions in the gas form and they came together and formed a solid, and a lot of energy is released because of the formation of those ionic bonds. So if we're looking at the heat of solution, that's the heat of the solute plus the heat of the solvent plus the heat of mixing. That's what we were just talking about. Now we're going to combine these 2 terms in and call this the heat of hydration, always negative, and delta H for the solute is always endothermic, always positive, because you're having to separate the solute particles. You still with me? So here we have an example of forming a solution between an aqueous solution of potassium fluoride. So separating potassium fluoride into ions in the gas state would be the reverse of the lattice energy. So when you take potassium and fluoride ions and allow them to form a solid, it releases 821 kilojoules for every mole. If you're going to separate them, you have to put in 821 kilojoules per mole. This is the heat of hydration term, where we've got those ions in their gas form, and we allow them to mix with the water, and this is going to release 819 kilojoules per mole of energy. The difference here is positive 2. So this is an endothermic process where it's absorbing 2 kilojoules of energy per mole. If the heat of solute is less than the heat of hydration, the process is exothermic. It's going to release energy, the solution will become warm. If this heat of the solute is greater than the heat of hydration, then the process is endothermic, and the solution will feel cold. So when we mix KF with water, is this going to be warm or cold? Is it absorbing heat or releasing heat? It's absorbing, because this is positive, right? We're taking the perspective of I am this solution. Is this positive for me? That means it's something coming in. So this means that energy is going into the solution that has to come from the surroundings, so this is going to feel cold.